This is your presenter Asloob Mudassar, and I am presenting slide number 88 of the course on laser physics. Question is, in question 83, we have seen that the field after one round trip represented by E prime of x, y, 2L in a two-mirror cavity is related to the initial field E prime of x, y, 0 through the relationship that is E prime of x, y, 2L is equal to sigma prime Lm multiplied by e to the power minus iota 2 kl multiplied by e prime of x, y, 0, where e prime of x, y, 2l are the eigen solutions and sigma prime Lm are the eigen values defined by sigma Lm is equal to 1 over a plus b divided by q, this whole term raised to power of 1 plus l plus m. ABCD is the transformation matrix for the forward and backward journey, that is for one round trip. The resonance frequencies were also given by nu Lmn is equal to C over 2L, and within parentheses we have n plus phi Lm over 2 pi. Express sigma Lm prime and nu Lmn in terms of phi, where phi appears in the expression sigma prime is equal to mod of sigma prime multiplied by e to the power iota phi. The answer is this presentation, which is presentation number 88, must be read with presentation 87. That is, you must go through the presentation 87 because many formulas are I am using from that presentation without proving in this presentation. So please have a look at the previous presentation. The answer is the complex beam parameter for a two mirror cavity was found as given, that is Q is equal to iota times square root of minus b over c, where the relevant ABC matrix was found as given. ABCD matrix is equal to, on the right hand side we have 2a1 d1 minus 1, second element is 2b1 d1, and in the second row the first element is 2a1 c1, and the second element of the second row is 2a1 d1 minus 1. So this is the ABCD matrix that we have derived in the previous slide. From here it is obvious that A is equal to D. You can see that the elements in the position A and in the position D on the right hand side are equal. So we can say that A equal to D for the matrix on the left hand side. Sigma prime 0, 0 as the fundamental mode may be denoted simply by sigma, where sigma is equal to 1 over A plus B over Q. This is also we have established in the previous slide, that sigma is equal to 1 over A plus B over Q, or we can write that sigma inverse is equal to A plus B over Q. Substituting the value of Q we get, you see that this is the value of Q that we just mentioned. So substituting this value of Q in this expression we get sigma inverse is equal to A plus B over iota times square root of minus B over C. So simplifying this one, we get A minus iota B times square root of minus C over B. And then on the rightmost side, we have equal to A minus iota times square root of minus BC. So this is what we have found sigma inverse. Now let's compute its magnitude, which is given over here. The absolute square of sigma inverse, because the sigma inverse is generally a complex quantity, so we need to take the absolute square of sigma inverse, and that is equal to, so you see that if you have a complex number, you know that how to compute the absolute square of that quantity. So calculating the absolute square of this quantity, we have a square minus bc. A square can be split into a, and then we have a minus bc. and one of the A can be replaced with D because we have the relationship A is equal to D. So replacing one of the A with the D, we have AD minus BC. And you know that AD minus BC is actually the determinant of this matrix, because the resonator that we have considered, for which this matrix was derived in the previous slide, and their both elements were in the same medium. So according to that one, the determinant of this matrix should be equal to 1. That is AD minus BC should be equal to 1. So the magnitude that we have found for sigma inverse, that is the absolute square of sigma inverse, is equal to 1. The corresponding diffraction loss represented by gamma is equal to 1 minus absolute square of sigma inverse is equal to 1 minus 1 is equal to 0, because the value of sigma in absolute square of sigma inverse is 1. So 1 minus 1 is equal to 0, and you know that gamma is what we have defined as the diffraction loss. Thus the diffraction loss gamma is thus 0. The physical reason for zero diffraction loss is due to the infinite size of mirrors in which the two mirror resonator. So in the two mirror resonator, if we assume the sizes of the mirrors to be of infinite extent, then we can find that the diffraction loss will be 0, because the light will be, after multiple reflections, will remain within the resonator and will not leave the resonator because of its infinite, because of the infinite dimensions of the mirrors. The initial and the final fields are related through sigma prime Lm. You see that here we have mentioned that the final the field after one round trip represented by E prime of x comma y comma 2L is equal to sigma prime Lm multiplied by e to the power minus iota 2k times L, and then the initial field, which is E prime of x comma y comma 0. So the final field and the initial field are related through sigma prime Lm. So the initial and the final fields are related through sigma prime Lm, which is why sigma prime Lm are known as the eigenvalues. We can write sigma prime Lm is equal to 1 over sigma 1 plus L plus M, and that can also be written as sigma inverse raised to power 1 plus L plus M. And you see that this is a sigma prime Lm is related to sigma through this relationship, because we have, you know, that sigma, we have this definition of the sigma is equal to 1 over A plus B over Q, and if you consult the previous slide, you will find there that sigma prime Lm is equal to 1 over A plus B over Q raised to power 1 plus L plus M. So that's why I have taken that relationship from there, and then I have correlated the two sigmas, that is the sigma prime Lm is equal to 1 over sigma raised to power 1 plus L plus M. And this can be written as a sigma inverse raised to power 1 plus L plus M. You know that sigma inverse or sigma is actually related with the fundamental mode of sigma prime 0 0. So for any other modes, that is the sigma prime of Lm is related to the sigma initial sigma through this relationship. That is the sigma prime Lm is equal to 1 over sigma raised to power 1 plus L plus M, and this whole can be written as a sigma inverse of 1 plus sigma inverse raised to power 1 plus L plus M. The magnitude of sigma prime Lm can be computed as given. You see that we have found the magnitude of sigma inverse in the form of absolute square of sigma inverse and has found that one equal to 1. So let's compute the mod value, that is the absolute value of sigma Lm, which is given by absolute square of sigma prime Lm is equal to the absolute square of sigma inverse raised to power 1 plus L plus M, because you know that if you take the absolute square of the quantity on the left hand side, you need to take the absolute square of the quantity on the right hand side, and you know that absolute square is taken for the complex quantities. So sigma Lm prime is generally complex and sigma inverse is also complex. So the absolute square of sigma prime Lm is equal to the absolute square of sigma minus 1, the absolute square of sigma minus 1. So that's why we have taken over here. And you know that sigma absolute square of sigma inverse is equal to 1. So 1 raised to power 1 plus L plus M is equal to 1. So it means that for any value of LMM, the absolute square of the sigma prime LM is 1. That is the magnitude of the sigma LM prime is also 1. To find an expression for the phase of the sigma prime LM, we proceed as given that sigma prime is equal to sigma prime mod e to the power iota 5. That is, a complex quantity can be written as the amplitude of that complex quantity multiplied by the phase term. So we have sigma prime is equal to mod of sigma prime multiplied by e to the power iota 5. Or this can be written as sigma inverse. Either you can omit the sign of a prime or you can keep the sign of a prime there. That would not change. But this sigma is the same as sigma prime. So sigma prime inverse or sigma inverse is equal to mod of sigma inverse multiplied by e to the power minus iota 5. And you know that e to the power a sigma inverse mod is equal to 1. So we have the final result that sigma inverse can be written as e to the power minus iota 5. And you know that the relationship that we used here, that is the sigma prime is equal to sigma prime mod e to the power iota 5 was given in the question. For example, over here. And you know that here I am using sigma prime. So sigma or sigma prime here both mean the same thing. And you know that here we have introduced phi over here as the phase factor, and we have to represent over quantities in this question. For example, the resonance frequency in terms of the phi of this phase factor. So that's why it was given in the question that we have a phi over here as the phase term. Using sigma inverse, which is equal to A minus iota times B multiplied by the square root of a minus C over B gives. So you see that we have sigma inverse from here, and we have also sigma inverse over here. Both are shown in red. So the two red quantities should be equal to each other because the left hand side of both are equal. So we have A minus iota times B multiplied by the square root of a minus C over B is equal to e to the power minus iota phi. So this is the expression, and we can compare the real and imaginary part of this expression. So comparing the real part, we get cos of phi is equal to A is equal to 2 times A1 D1 minus 1, and the imaginary part will give you sine of phi is equal to B times multiplied by the square root of a minus C over B. And if you represent C and B in terms of the A1, B1, C1, D1 matrices, then you will have sine of phi is equal to 2 times of B1, D1 multiplied by the square root of minus A1, C1 over B1, D1. So we have two expressions giving you the information about the value of phi. Because we want to investigate the value of phi, what is phi is. Because ultimately we have to represent our quantities of interest in terms of phi. So it is better to know something about the value of phi. Where A1, B1, C1, D1 are the matrix elements of the forward journey as given in slide number 87. From equation 88.2, that is from equation number 2, this is the equation number 2, and from this equation it follows that phi should be in the range of minus pi to plus pi. But when B1 D1, you see that this is the term A1 C1 over B1 D1 is what we have also discussed in much greater detail in slide number 87. And we found that the square root containing minus A1 C1 over B1 D1 is always a positive term. So we don't bother about this term, and we shall bother about the terms within the outside that one, which is B1 and D1. So when B1 D1 is greater than 0, then phi will lie in the range from 0 to pi. And when b1 d1 is less than 0, then phi will lie in the range from minus pi to 0. Now the question is that, as I said, that the square root as shown in equation number 2 will always be a positive quantity. So if it is a positive with the b1 d1 greater than 0, then how it could be positive when b1 and d1 is less than 0? The question is that in that case a1 and c1 will also change sign such that the square root containing minus a1 c1 over b1 d1 will always be a positive quantity. So the sign will only be decided by the term b1 d1 outside the square root. So that's why we have computed the range of phi using b1 for b1 d1 greater than 0 and for b1 d1 less than 0. Let's find an expression of phi using equation number 1, that is this equation. We can write cos of phi is equal to 2 times cos square phi by 2 minus 1, and this is equal to 2a1 d1 minus 1. So you see that here we have represented cos in the form of square using half angle representation. And from there you can find out, from here you can find out the value of phi, which is equal to 2 into cos inverse of plus minus times the square root of a1 and d1 as shown in equation number 3. So you see that we have discussed the ranges of phi for different values of b1 and d1, and we have also given an expression in equation number 3 for the value of phi. To represent sigma prime Lm in terms of phi, we start with the given relationship, that is sigma prime Lm is equal to 1 over a plus b over q whole term raised to power 1 plus L plus m, which can be written as a plus b divided by q raised to power minus times 1 plus L plus m. And you know that we have represented 1 plus b over q as a sigma inverse. So sigma inverse raised to power minus times L plus 1 plus L plus m. And you know that we have represented that sigma inverse is equal to e to the power minus iota phi. For example, in this relationship we have established, look at this relation. On the left hand side we have sigma inverse, on the right hand side we have e to the power minus iota phi. So using this value in terms over here in respect of e to the power minus 1, we have e to the power minus iota phi, then raised to power minus times of 1 plus L plus m, and then the final result is e to the power iota phi multiplied by 1 plus L plus m. Now this phi with multiplication of 1 plus L plus m can be simplified and can be represented as phi Lm. So sigma prime Lm is equal to e to the power phi Lm as shown in equation number 4, where phi Lm is equal to phi times 1 plus L plus m. The given resonance frequency equation takes the following form. So let's look at the resonance frequency that is given in the question. Nu Lmn is equal to C over 2L plus within parentheses we have n plus phi Lm over 2 pi. So you see that here we have found an expression for the value of phi Lm. And that expression is given in equation number 5. So replacing phi Lm in the resonance frequency expression given in the question, we are now rewriting that expression over here in terms and replacing the value of phi Lm by the value on the right hand side given in equation number 5. So the resonance frequency becomes nu Lmn is equal to C over 2L. Within the parentheses we have n plus phi Lm over 2 pi, and then we have C over 2L multiplied by, within parentheses we have n plus 1 plus L plus m divided by 2 pi, and this term is being multiplied by phi. We can also represent phi by its expression we have found in equation number 3, that is phi is equal to 2 times cos inverse of, within parentheses we have a plus minus times the square root of a1 and d1. So replacing phi in this expression, we obtained the final result as nu lmn is equal to c over 2l. Within the parentheses, we have n plus 1 plus L plus M divided by pi, and then we have cos inverse of, within the parentheses, we have a plus minus times the square root of A1 and D1. So this expression is in terms of phi, and this expression is in terms of the matrix elements A1, B1, C1, and D1, out of which only A1 and D1 appears. A1 and D1 appears in the equation number 8, in the equation number 6. If B1 D1 is greater than 0, you see that here we have two signs, plus sign and minus sign. So if B1 D1 is greater than 0, then plus sign is chosen. And when B1 D1 is less than 0, then the negative sign is chosen. We have worked out the A1, B1, C1, D1 matrix for the two mirror resonator as given. And we have given that one in terms of the G factors. So A1, B1, C1, D1 is equal to, in the first row, the first element is G1, the second element is capital L, which is the resonator, which is the spacing between, or which is the length of the resonator. And in the second row, the first element is minus 1 minus G1, G2 divided by capital L, and the other element is G2. So for this one, for the derivation of this one, you can consult equation number 7 of the previous slide. So from that one, we can get A1 D1. So you see that if you multiply A1 D1 from the matrices on the left hand side, and then you need to multiply the corresponding elements from the right hand side. So A1 D1 is equal to G1 and G2, because we have A1 and D1 present here in equation number 6. So if you substitute that value over there, you will get the resonance frequency in terms of the G, in terms of the G factors of the cavity. So nu Lm is equal to C over 2L. Within the parentheses, we have n plus 1 plus L plus M divided by divided by pi, multiplied by the cos inverse of parentheses containing plus minus times G1, G2, square root of G1 and G2. So here we have expressed the resonance frequency in terms of the G factors containing G1 and G2, the square root of G1 and G2. And you know that G1 and G2 is what we have given a relationship in terms of the matrix elements A1, B1, C1, D1. So you see that we have represented our resonance frequencies in different expressions. Here we have given the expression in terms of phi. Here we have given the expression in terms of the elements of the A1, B1, C1, D1 matrices. And only two elements A1, D1 appears over here in equation number 6. And then in terms of the G factors, we have also given the relationship as shown in equation number 7. So positive sign is chosen when B1 D1 is equal to L times G2 is greater than 0. So when B1 D1 is greater than 0, which means that L times G2 is greater than 0. And this also implies that G2 is greater than 0, because L is always a positive quantity, the separation between the two cavity mirrors. So this is what we have briefly expressed over quantities, especially over here, the resonance frequencies in terms of the required quantities, especially the phi, and then the matrix elements of the A1, B1, C1, D1 matrices, and then in terms of the G parameters of the resonator. So this completes our answer. So this is the end of slide number 88.